Our next example relates to applying trigonometry in the delivery of radiation for cancer treatment, but localized delivery at a select location on the person. So let us go ahead and draw a schematic, because with the schematic we'll conceptualize the problem and then try to apply trigonometry in identifying these issue that we are going to discuss. So I will go ahead and use again schematics as before. I was going to say here I have a person that is lying on a table, and this person has cancer that is at this location. And the way that the radiation treatment is delivered is through a beam. And the beam mechanism is attached at the end of a large robot. So let me go ahead and draw the schematic of a large robot. Is not a, so we have this robot, and at the end of the robot there is this head, and in this head we have all the equipment that generate the radiation. So we would like to have this head pointed to the cancer location. And we are going to make a couple of assumptions: that the robot is positioned and all its joints are fixed, and the only one that moves is this head that could rotate about this point. Okay? So our goal is to position the head in the rotation angle. Again, we are working on a plane to hit the target. And the target is the cancer. So what I'm going to do, I'm going to take this physical problem now, this description, and represent it with a schematic. And we are not going to show the person, we're not going to show much, but let's show the target, which is the cancer. Actually, let's draw it down here. Here is the cancer. And then let us also draw the head and the ray that is being generated by the head. So if everything is great, the ray will hit the target. However, if there is an error in the positioning of this head, let's say an angle theta, where will the ray hit? And here we are exaggerating this. Okay, we are exaggerating this to show that there is an error in the angle. So here there is an error of an angle theta, and of course the angle theta could be an error on the other side, but we will perform the analysis only on one side. If we know the distance between the head and the target, let's call this L, we are interested in finding out this offset here, which means that the ray will hit at this location now, location B, instead of the original location where is the target. So now we would like to apply trigonometric theory to find out this offset distance. because if the ray hits a point B, it will be destroying healthy tissue instead of the cancerous area. So now we have these two sides of a triangle. We have the included angle, and we are interested to find the opposite, the length of the opposite side. So because this angle theta is usually small, there is an assumption we can make that this represents a right angle triangle. And we can write the relationship as the sine of this angle theta will be equal to the area here. Let's call this delta L, the offset in the distance, divided by the original length, L. So the offset in the distance, delta L, will be equal to the original distance times the sine of this angle. So now we can put numbers and say that if the original length is known, and we know the angle theta or the error in positioning of angle theta or rotation of angle theta, we can solve and find out where the radiation rate will be delivered. The other approach we can say is the following, is the inverse problem in defining the equipment, the capability of the equipment that will be used in delivering this radiation. Let us assume that we know delta L. We know what is the maximum offset that can be accommodated. Okay, let's say it's 4 millimeters, 5 millimeters, the 1 centimeter. That's an error in or allowable area where allowable distance where the ray could hit. So let us rewrite our expression. Delta L over L equals sine theta. So now we know the allowable error in the location where the ray needs to hit. We know the original distance between the location where the ray starts and the target, and we can use this relationship to find out sine theta. And of course from here, I can find the angle theta. In reality, this angle theta relates to the error in measuring the angle. So here, we can come and say the capability of this robotic equipment that carries the head, or the capability of the rotating the head, must be such that theta is less than theta, the original theta here, let's call it theta maximum. So if theta maximum is 1 degree, then our hardware must have better resolution in measuring that angle. And of course, 1 degree is exaggerated, but that gives you an idea of how these trigonometric principles could be employed in finding both delta L and also defining capability of equipment in order to deliver the radiation as close to the target as possible such that it will not kill or destroy any healthy tissue.